In 9.5, we actually proved the alternating series test. And the gist of it is this. If we have an alternating series, every other term is positive and every other term is negative. Where a sub n is the part that has nothing to do with the sign, it's always the part that's bigger than 0. If these two criteria are met, if every a sub n is smaller than the one in front of it, or equal to, and if the a sub n terms tend towards 0 as n tends toward infinity, then we know for a fact that this series will converge. For our first example, we looked at not the harmonic series, but the alternating harmonic series. A sub n is 1 over n, and this is going towards 0 as n goes toward infinity. And we can easily show that the nth term will always be less than or equal to the previous term. There's the nth term and the previous term, and quickly we can solve algebraically that this is always true. Since the two criteria are met, our series converges by the alternating series test. This next example is a bit trickier. Notice it doesn't have the -1 factor. And so our first step will be to rewrite this so that we can isolate the alternating sign part of it. All right, so if we focus on this expression and ignore Orange Julius the cat, we will rewrite -2 as -1 times 2, and then we'll use the power of exponents where each factor gets raised to the n-1 power. For -1 to this power, it's either 1 or -1. It doesn't matter if it's in the numerator or the denominator, so we'll rewrite it on top. And that leaves us the alternating component multiplied by the ratio of n and 2 to the power of n-1. All right, so this is our series. Let's check the conditions. This is an alternating series. The a sub nth term is in blue, and as n goes toward infinity, the a sub nth term does go to 0. Check. Next condition, is the nth term always less than or equal to the previous term? So that's asking when n is just n, will that a term be less than or equal to the a term when the subscript is n-1? So n-1 over 2 to the n-1 minus 1. That gives us this inequality. Let's multiply by a power of 2 that has the bigger of these two exponents on it. And when we do that, we'll be left with just n is less than or equal to n-1 times 2 to the n-1 on top over 2 to the n-2 on the bottom, which gives us just that. And solving this nice little linear inequality yields that it's true. All the terms are getting smaller as long as n is greater than or equal to 2. So we can check this box, and now we can conclude that our series converges by the alternating series test. Remember that this may not have been true from term 1 to term 2, but that's okay. Term 1 is one finite term. For the rest of the infinite terms being added together, the conditions are met, and we're good. All right, take a look at this example. Remember, when you have a series and we ask you, does it converge or diverge, you can use any method we've learned. So you don't need to use the alternating series test for this alternating series, although you could. When I look at the series, I see that the numerator is increasing at a linear pace, and the denominator is increasing at a logarithmic pace, which is much slower than a linear pace. So I can see in this case that the limit of a sub n is infinity, which is not 0, and therefore the series diverges by the nth term test for divergence. A more interesting series might be this one. So now the denominator is increasing more quickly than the numerator, so the nth term is going to 0. It is an alternating series, so if we can just prove that the nth term is less than or equal to the previous term, then we will deduce convergence by the alternating series test. Does a sub n go to 0? Yes, it does. Is every term getting smaller than the previous term, smaller or equal to? For this, let's use calculus. And let's find f prime of x. So using the quotient rule, this is the first derivative. We need to know when that's negative, showing the function is decreasing. This would be negative when the numerator is negative. And moving on, so when is x smaller than the product of x plus 1 and the natural log of x plus 1? Keep in mind x values are 1 or bigger, so this factor is going to be 2 or bigger. And so when x is, let's say 1, is 1 smaller than 2 times the natural log of 2? Well, the natural log of 2 is about 0.6. So 0.6 times 2 is about 1.2, so the answer is yes. So this is true. Our terms are getting smaller, and we're done. This series converges by the alternate series convergence test. All right, enough examples for that. Let's move on to the next idea. How close is any partial sum to the infinite sum? In other words, if we stopped at, for example, the fourth term, how close would that fourth partial sum be to the infinite sum? The magnitude of that difference is considered the error, or, as we've seen before, the remainder. R sub n is the remainder or the error between our partial sum and the infinite sum when our partial sum stops at the nth term. We've talked about this in previous homework problems, but now we're asking about this question when the infinite series is an alternating series. Well, the answer to that question is found in the alternating series remainder theorem. We aren't going to prove that here in this video because I'd rather keep the video short, and we'll leave that proof to class. They don't prove it in the textbook, so we'll have to do it on our own. But here's what it says. It says for an alternating series that converges. We should say an infinite alternating series that converges. And the difference between these two is just whether the first term starts as the negative term or the positive term. So for a converging infinite alternating series, the bound of the error when you stop with an nth partial sum is the first term that you didn't use. That's it. What does this mean? Well, what about this series? We know that 1 over n squared all by itself, with all positive terms, converges to pi over 6. We didn't learn why yet, but you'll have to take my word for it. Well, the alternating series is definitely going to converge. And how close will our, let's say, our fourth partial sum be to the infinite series? Let's find out. So the fourth partial sum is 0.79861 repeating. How close is this to the infinite sum? That's where the alternate series remainder theorem comes in. And it says that the remainder, when we use the nth partial sum, is no bigger than the first neglected term, which in this case is 1 over 25. I'd like to make that observation one more time, which is the bound of the error is the first neglected term. And when we say the first neglected term, we're not including whether it's positive or negative, right? A sub n plus 1 comes from this expression, not the alternating factor, just the expression 1 over n squared. So the fourth partial sum stops with a sub 4. So a sub 5, which is 1/25, is the upper bound of our error. That's it. Finding the bounded error for alternating series that converge is really easy. You just take the first neglected term, in this case 1/25, and we know for a fact that our partial sum is no more than that amount away from the infinite sum. All right, for the last example, this is the type of problem where we say how many terms would it take to get a partial sum that estimated the infinite sum of the series to within 1/1,000,000th of a unit. Well, n is how many terms it would take so that the partial sum will estimate the infinite sum to within 1/1,000,000th of the actual value. So find n. Well, the remainder theorem, the alternating series remainder theorem, says that this error is bounded by the first neglected term. Well, this error corresponds to the nth partial sum, which means the first neglected term is the n plus 1th term. Well, the n plus 1th term is equal to 1 over n plus 1 squared. And we know that this needs to be an error that's within 1 over 1/1,000,000th. 1/1,000,000th. So when we solve this inequality for n, the n value that makes this inequality true is the n value such that the partial sum has an error that's less than or equal to 1/1,000,000th. Here we go. N plus 1 squared will have to be greater than or equal to 1,000,000. We take the square root of both sides. N plus 1 is greater than or equal to 1,000. So as long as n is greater than or equal to 999, our remainder will be less than 1/1,000,000th of a unit. So the answer is 999 terms. If we had solved this inequality and ended up with n is greater than or equal to 999.3, if it didn't come out to a nice whole number, then 999 terms wouldn't be enough. And in that case, we would say that it would take 1,000 terms. But in this problem, it came out with a nice whole number. As long as n is greater than or equal to 999, our partial sum with that many terms will have an error that's less than 1,000,000.